Hello everyone, you're welcome to my YouTube channel. I am Ridwan Ibrahim. In this video we will be making a structural analysis of the steelwork that is shown. We will be making some simple designs, and then we will be having it in 2 episodes. First, I would like to apologize for the late update. It has been long ever since I last make a video on my channel. I've been so busy. Even this particular one that I am making right now, if you see the date here, you will see that it has been since November 2023. So I've actually prepared this document since 2023, but I've been quite busy to make a video on it. So this is a steelwork of a filling station. It's just a picture I picked online. The objective of this is that we will be carrying out the structural analysis of the steelwork that is shown above, and then we will design a suitable base plate and bolt connection for the universal column. So what we just need to do here is that we want to make the structural analysis of base plates, and then we want to have a bolt connection. Okay, so we want to design a base plate and want to have a bolt connection. All right, so that is our major concern. So any form of analysis we do is just to get the reactions that we will use to design our base plate and our bolt connection. All right, you can see that the whole of everything going on here, like this whole frame, right? This whole frame is being carried by a beam, so which is this beam, and also this beam. So there are 2 beams carrying all of those flat frame, right? And then the beam, the load of the beam is now transferred into these 2 columns, which is this column and then this column. All right, so underneath this column we expect to have a connection to the concrete here. All right, so there will be a connection between this steel column and this concrete planes. So the connection that is expected to be there is a base plates and bolts connection. You know, we have anchor bolts going into the planes. So that is exactly what we want to design. We want to design a suitable base plate and we want to have a bolt connection. All right, so that is the objective of this. Now these are the known parameters. So the column section, as I mentioned, column is a vertical element and there are 2 in number, this and this. They are the column. All right, and then this horizontal one at the top of the column, which is this one, and then this one, they are the beam, right? And then all this nested hole, this one underneath, and then even this top parts, that, you know, all those plates, they are the top loads. All right, which is eventually being transferred into the 2 columns. So the column section, we have them 2 in number. The section is 203 by 203 by 46. That is a UC column, right? And then beam, we have 356 by 360 by, I guess I wanted to use 356 by 356. So we are just going to make a simple change here. Okay, so this is meant to be 356 as well, 356, because I want to use UC, not UB. Plates, the plate is given to be 400 mm by 10 mm. Okay, so basically the plates, so this surface here, okay, which is the top surface where you have this nested hole, and also even this big surface here, all of this, they are plates which is 400 mm high, and the thickness of the plates is 10 mm. All right, so that is what is given here. And then the dead load of the plates, unfactored dead load of the plate, is given as 10 kilonewton per meter. 10 kilonewton per meter is quite high, so we can have something like maybe 10 kilogram per meter, but I think this was a mistake for me. I wanted to write 10 kilogram. Maybe we will change that. We can just keep using the 10 kilonewton per meter, even though it's quite high. The average drag coefficient is 1.5. The wind pressure is 0.85. The live load is 2 kilonewton. You might be wondering what kind of live load can you have here. Well, you have live load because it is a filling station, and then there are always lighting points. All the lighting bulbs for brightness at night and all. So you definitely need some fixings on this canopy. So all that all that are classified as live load, and even the rainfall, and then maybe some kind of maintenance when you have people coming in. So we can all just round all that up as live load. And then FCU is did I use 15 here? Wanted. Let me just something like 30. Okay, FCU 30. That is the grade of concrete. Okay. So as you have seen before, this is the plan view, right? So this is the north side. So we have the plan view. So if you look at this very well, so just imagine you are looking at it from the top. Okay, so that is what I mean by the plan view, right? So if you are looking at that from the top, you see this is our UB, not UB, it's UC. This is our beam, right? This beam and this beam, and then this is our column. We have this column, and we have this column, and we have all of this side as plates. Even this one, all these 4 sides, we have the vertical plate as well. So this long side of the canopy is 12 meter, and this short side of the canopy is 8 meter. Okay, and then this is the west elevation. All right, so this tells you that the height of the column is nothing but 5.5 meter, and you can see your beam being shown a little bit over here. Okay, and the canopy, the height of it here is 400 millimeters, which is the same thing as the height of the plate as given. Okay, so we have 3-meter span here, from here to here. We have 3-meter span from here to here, and we have a 3-meter span from here to here. So that's equivalent to 12 meter, as you can see here. Okay, so the 12 meter here. Good, right? And then if you check the north elevation, so we have 3.5 meter here, and we have 4.5 meter here. Okay, from this position up to this position is 3.5 meter. From this position up to this position is 4.5 meter. So that accounts for the 8 meter. All right, so also from this position up to this position, 3 meter. From this position up to this position, 3 meter. And from this position up to this position, 6 meter. So that accounts for the 12 meter. All right, so that is what this elevation is just showing you. And then it also shows you the height of the column to be 5.5 meter, and it shows you the height of the canopy to be 400 millimeters, which is equivalent to 0.4 meter. All right, so my loading calculations. Number 1, unfactored load of the plates. The unfactored load of the plates will be 10 kilonewton per meter. The dead load, unfactored dead load, has been given to be 10 kilonewton per meter, which I made the comment that it is quite high, but let's just use it for uniformity. So so I am going to multiply that by the factor of safety for dead load, which is 1.35. This is for Euro code. I think for BS code is usually 1.4. So if I multiply this, that should be equivalent to 10.35. I think, sorry, 13.35, 13.5. Yeah, that should be 13.5 kilonewton per meter. The unit will still remain because this is just number, no unit change per meter, right? So I just factor it. The second load is the weight of the beam. Okay, so the weight of the beam is supposed to be 129 kilogram per meter. When you have a section and it is stated to be 356 by 356 by 129, okay, and say it is a UC. So basically what that means is okay, when you have Okay, so your B, this is B, your B is 356. Okay, and then your D, big letter D, is 356. Okay, and then when you check it in the long elevation, the longer elevation, so per meter, 1 meter run, the weight is 129 kilogram per meter. So that is basically what this means. So this is in millimeter, this is in millimeter, and this last one is in kilogram per meter. All right, so I believe that is quite easy. So the unit weight is 129 kilogram per meter, and then definitely I need to multiply that by 9.81 so that I can convert that to Newton, right? You know, Newton per meter. So it's now in Newton per meter, and then I will multiply that by the factor of safety for weight. So the factor of safety for weight is 1.35, and so all that should give me 1.71 kilonewton per meter. Okay, so thirdly, I will determine what the surface area of the plate is. Okay, so the front area. Why am I calculating the front area? Because I will need to calculate the wind, so and I need the area to do that. So front area of the vertical plate, front area, let me say front area of the vertical plate, so that will be equivalent to 12 meter, and then I will multiply that by the height of the plate, which is 0.4 meter. So that is the surface area, and that will be equivalent to 4.8 meter square. I think that is good enough. So I need to calculate the wind force. So the wind force, that will be the wind pressure. The wind pressure has been given to be 0.85 kilonewton per meter squared, right? So the wind pressure multiplied by the surface area, which is 4.8, so multiply by 4.8 meter squared, and then the wind force I have to multiply by the drag coefficient, which has been given to be 1.5. Also, don't forget that wind load is a live load, so I will be multiplying that by 1.5 instead of 1.35. Okay, is a live load. If it is a dead load, you multiply by 1.35. 1.5, and all that will give me 9.2 kilonewton. So that is the wind force. But this is not the force on the column, this is the force on the plate, right? Because you can see I multiply by the front area. I don't know if what I'm trying to explain here is quite clear. Maybe I should just bring in the image one more time. So this is what I'm trying to explain. You know, when you have wind force, you have wind force eating on this surface. You know, wind force on the surface. Okay, right? So all of this wind force will just be resulted in a simple point load when we want to make our analysis. So the wind force on this plate is what I just analyzed, what I'm trying to calculate. That is why I looked for the length of this plate, which is 12 meter, and then the height of this plate, which is 0.4 meter. So that is the area, and then I use that to quantify the wind force on this face. Also, you also need to quantify the wind force on the column, okay, because the column is also a vertical element that will be receiving wind load. So you kind of need the length and then the height of the column. So you need the surface area for the column, and then we are going to make the same kind of calculation so that we know the wind force on the column. Okay, so that is the wind force I just explained. And the fifth thing right now is that let me see what is the live load. Okay, so the live load has been given to be 2 kilonewton per meter. So 2 kilonewton per meter, I just need to multiply by the factor of safety, which will be 1.5, and that will give me 3 kilonewton per meter. That is my live load. The total load of canopy, which is plate. So that will be equivalent to this one, 13.5, which is the unfactored load of the plate per kilonewton. Yeah, right. So that will be 13.5 kilonewton per meter, and then I will have to add it to the live load. Okay, so plus 3, right? Plus 3, and that will give me 16.5 kilonewton per meter. So this is like the design load, because it's the addition of the dead load and the live load. So to make it easy without jumping around, it can be seen from the image that the weight of the canopy is single-handedly carried by just 2 beams. Okay, the 2 beams is the one carrying the weight of the canopy. So since there are 2 beams carrying the canopy and they are carrying it at equal distance, we can simply say that the load on each beam will now be equivalent to 16.5 kilonewton per meter divided by 2. Okay, because there are just 2 beams carrying the canopy and they are carrying it at equal distance, so you can just divide the load by 2. All right, so 16.5 divided by 2, that should be 8.25, I think. Yeah, so that should be 8.25 kilonewton per meter. So this is the weight on the beam, but this does not include the weight of the beam itself. It's just the load on the beam from the canopy. Okay, so the total load on the beam should be the load from the canopy, including the weight of the beam itself. All right, let me say total load on each beam. That will be 8.25 plus the self weight of the beam itself. Okay, so which is 1.71. okay, so plus 1.71, and that should give me 9.96 kilonewton per meter. Okay, so this is the total load on each beam. This is now the load that will now be transferred into the coulomb. All right, so what other load do I need to calculate? Okay, I think there is more. Let me say item 6. I need to calculate the wind load on the coulomb. Just as I mentioned, I have one wind load that is hitting the front surface of the plate, which is the vertical one, this load that I've calculated as I explained earlier, and I also have a wind load that is now applied to the coulomb itself. Okay, so I need the area of the coulomb, and I also need the area of the coulomb. So I'll just calculate all that together. So wind load on coulomb, so that should give me 0.203 multiplied by the height of the coulomb, 5.5. so the 0.203 multiplied by 5.5, that is the surface area that the load will be hitting. Don't forget 5.5 is the height of the coulomb, and 0.203, that is the section of the coulomb, because the coulomb is 203 by 203, right? So this is the surface area the wind load will be hitting, and then that is the surface area. So I need to multiply that by the wind pressure, which has been given to be 0.85, and then I need to multiply by the drag coefficient, that is 1.5, and because it is a live load, I also need to factor it by 1.5 according to Euro code, and this will give me 2.14 kilonewton. Is that correct? Yes, 2.14 kilonewton. So that is the wind load on the coulomb. All right, also I have not calculated the self weight of the coulomb. So weight of coulomb, I've calculated the wind load of coulomb, so I need the weight of coulomb itself. So the UC beam of the coulomb is 203 by 203 by 46. Okay, so so I'll just calculate that. So 46 kilogram per meter multiplied by 9.81, so I can convert that to Newton per meter, and then multiplied by the height of the column, which is 5.5 meter, and then it is a dead load 1.35. I'll factor it by 1.35, and that should give me 3.36 kilonewton. So that is the weight of the column. So I think this is all of the weight, this is all of the loads that we need to calculate, so we can easily say we are done with the loading calculation. So we can easily move to the other part. So let's see our load. First, we calculated the unfactored load of the plate, which is the weight of the plate. It has been given to be 10 kilonewton, so just multiply by the factor of safety, that's 13.5. Also the weight of the beam, self weight of the beam, 1.71. The front area of the plate is 4.8 meters squared. The wind force on the plate is 9.2 kilonewton. The live load on the canopy and everything is 3 kilonewton, and then the total load of the canopy, okay, is 16.5. Now the canopy is being carried by 2 beams, so we have to divide this by 2. This is the load that will go onto each beam, so that is 8.25. And the total load on each beam, which we expect to include the weight of the beam itself, is 9.96 kilonewton per meter. The wind load on the column is 2.14 kilonewton, and the weight of the column is 3.36 kilonewton. All right, so if that is good, then we can move to the next step. So let's see in the next episode.